Hi again everyone, Chris Tisdale here again. In this presentation I'm going to continue my series of videos that give a gentle introduction to the mathematics of vectors. Now in this particular presentation I'm going to introduce two special vectors, the I and the J vectors known as the basis vectors, and I'm also going to introduce what's known as a column vector. And we'll learn a little bit about the algebra of addition, subtraction, and scalar multiplication of these column vectors. Now, before we get down to that, in the previous video, I introduced a vector and we talked about the geometry of vectors and vector addition and scalar multiplication. So I'm just briefly going to go over that before we get to my new presentation. So you don't need any knowledge about vectors to follow along with this presentation, but the basic class that I gave last time motivated the ideas, and we defined a vector to be a quantity that has a length and a direction. And geometrically speaking, a vector is just a line segment that is basically has a head point and a tail point. The head point would be up here and the tail point would be down there. And essentially we just refer to it as a directed line segment. And then we talked about the geometry of vector addition and subtraction. You have a parallelogram rule or a triangle rule, and you can draw the vectors in such that you can geometrically represent the sum of the two vectors. And if you multiply, say, a vector by a number, you can stretch, compress, flip, or do all three, depending on what that number is. Okay, so if you want more on that, then I'll refer you to the previous video in this series, the very first video. Okay, so on to this particular presentation. Now, some people, if you watch that previous video, they'll be thinking, hang on, if this is how you define a vector, something with a magnitude or a length and a direction, that sometimes leaves people a little bit curious about what a vector really is. So the first part of this presentation is basically designed to answer the question, but what is a vector? And essentially I'm going to write vectors, not just as the sort of boldface kind of boldface or tildes or arrows type expressions. We're going to write them as columns. Okay, so I'm going to introduce two very simple vectors that we give special names. The I vector is written as a column in this way, and the J vector is written as a column in this way. So let me just draw them for you. The I vector is a special vector that points, that points horizontally and to the right. And it has length 1. And the J vector points vertically up and also has length 1. Okay, so forget this little squiggle here, that's nothing. So this vector I always points to the right and is, I guess, horizontal. This vector J always points up and they both have length 1. Now, if you might think, well, what does 1, 0 and 0, 1 have to do with anything? Well, if I draw in say part of the xy plane. So here's the vertical y-axis, here's the vertical x-axis. And I go out 1 unit along the positive x-axis, and say 1 unit along the positive y-axis. And I draw a line segment joining the origin, so to those points. You can see that this point is the point 1, 0. And this point, where the head of the vector is, or the head point, is the point 0, 1. Now, if we write those as columns, you get this would go to this, and this would go to this. Okay? Now, these are points, so we write them kind of as an ordered double. These are columns. So by writing these as columns, we're representing the vector from the origin to the points associated with these 1, 0, and 0, 1. Okay? So these two special vectors are going to be very important in our discussion and introduction to vectors, the I vector and the J vector. Now, a really important property of the I and J vectors is that any vector in the XY plane can be written in terms of I's and J's, just using the triangle law of addition and scalar multiplication. Now, I'll talk a bit more about that later, and I'll give you a little animation to sort of get you into the spirit of things. But let's just talk a little bit more about this column form. The column form of a vector A in the XY plane is given by this, okay, where A1 and A2 are numbers, I and J are our basis vectors, and you can write them as this, and actually this is the column form. Okay, so if I was to specify the column form, it would be this thing over here. But I've just sort of broken it down to show you how you can break any vector down into the I and J component vectors, if you like. So for example, suppose we're talking about the column vector 3, 2. Well, that's just 3 times I plus 2 times J. Okay, now some books always use columns and column vectors. Other books tend to use the I's and J's. That's why I'm sort of writing them together to get you into exposed to both settings. Okay. Now you might think, well, what's the geometry here? Well, it's just the triangle law and the scalar multiplication law. If I have a vector up here, I can just stretch the I vector, stretch the J vector, and through scalar multiplication, and then add them to get any vector I like in the XY plane. And I'll show you an animation about that later on. Okay, so how to add, subtract, and scalar multiply vectors. Now, we've already talked about this in the previous presentation, but it was all geometry and geometrical arguments using triangle inequalities, parallelogram rules, and stretching and compressing through scalar multiplication. Here, I'm just going to show you the algebra of how to do it. Okay, so let's talk about addition and subtraction first. Oh, this should be vectors, sorry, not complex numbers. Okay, so to add or subtract two vectors, just add and subtract their corresponding components. Okay, so suppose we have two vectors here, A and B. Then if I wanted to add A and B, and I'm just using the column forms here, you would just add the first component with the first component. So 3 plus 5 is 8. That would be the first component of the sum. You add the second component with the second component. 4 plus 6 is 10. That would be the second component of your column vector, which represents the sum. If you wanted to take away or subtract A minus B, well, you subtract again the corresponding components. 3 minus 5, negative 2. 4 minus 6, negative 2. Okay? Now, if I wanted to multiply a scalar, or just a number, with a vector, just multiply each component by the scalar. So for example, let me just squeeze this in over here. For this vector A, let's say I wanted to multiply that vector by 3. Now I know that geometrically this just involves stretching the vector by a factor of 3. But if I'm just multiplying here algebraically, what I would do is multiply the first component by the number 3, so I get 9. Multiply the second component by the number 3, and I get 12. And that is my column vector, okay, which is the product. Okay, what about this kind of situation? Here I want to compute 3 times A plus 2 times B. So it's 3 times A, which I have up here, plus 2 times B. So again, you would just multiply in a component-wise fashion. So 3 times 3 is 9, 3 times 4 is 12, like we had up here, plus 2 times 5, 10, and then the second component will be 2 times 6, which is 12. Add the corresponding components. 9 plus 10 is 19, 12 plus 12 is 24. Okay, so that's the basic algebra of adding column vectors. Now, you might be thinking, well, what happens if the vectors are expressed in terms of i's and j's? Can I do something there? And the answer is yes. So let me show you how I've done that with the unit vectors I and j. You again just add the corresponding i's together and the corresponding j's together. So 3i plus 5i is 8i, 4j plus 6j is 10j. Okay, same with the other two cases. 3i minus 5i is negative 2i. 4j minus 6j is negative 2j. Okay, you keep on going. All right, so here I've used the i's and j's. Okay, so I'm now going to talk about what I mean by a position vector. Okay, so and I'm going to use a specific example here. Suppose we have a vector that has its tail point at the origin and its head point at the point 2, 3, which I've denoted by A. Now the vector form, that vector there, is called the position vector A of the point big A. Okay, so the other, we can write it like this, or we can write it to hammer home that it's from the origin to a point A. We can write it as this kind of OA with an arrow above it. Now I can do that for any point in the XY plane. I can always form what's known as a position vector to any point there. And again, if I draw in, say, my basis vectors, my unit basis vectors, because they have length 1, then I can see that to get out to here, I need to multiply I by 2, and I'll get that stretch there. And to get up here, I've multiplied j by 3. So using the triangle rule, it would be 2i plus 3j. Okay, so you draw in a sort of right-angled triangle here. And the hypotenuse would be the sum. Okay, so when we talk about a position vector, we can always draw the tail point of the vector at the origin and the head point at the point in question. Okay, well that's pretty much all I wanted to talk about in this presentation. It's been a pretty short one, and the focus has been on the following. I wanted to introduce the idea of these unit basis vectors, I and j, and then the column form of a vector. And then I just wanted to talk a little bit about the ways you can, like the algebra or the actual mechanics of how you add, subtract, and scalar multiply vectors. Now, I wanted to come back to this claim in here. Any vector in the xy plane can be written in terms of I and j using a triangle law and scalar multiplication. Okay, so I wanted to show you a little GeoGebra animation for that. And let me see if I can put that on. Okay, here we are. So you can see I've got the green vector here, which is the unit vector I, and this sort of yellowy orange unit vector j here. And then I've got this purple vector u. Now, I've just introduced these a and b. U, the vector u, is the number a times I plus the number b times j. Okay, and what I'm going to do is vary a and b, and you'll see what happens to u as we vary a and b. Now I'm just varying a and b between -5 and 5. Okay, so you can see what's happening now with u. U's kind of turning around, it's growing, it's being stretched, it's being compressed, and this should, although this isn't a proof by any means, this should give you an idea and hopefully should convince you that I can describe any vector in the xy plane via a combination of these I and j vectors. Okay, what's known as a linear combination. Okay, so that's the end of my presentation. Thanks for watching. In the next presentation, I'll be talking about how we can measure the length of vectors, how big is a vector, and also how we can measure the direction or the angles associated with vectors. So I hope you can join me for those presentations. If you have any feedback, let me know, post comments in the comments section below. So I hope you can join me for the next presentation in this series of an introduction to vectors. Bye.